Welcome to the deep dive. Today we're exploring a really interesting new angle on understanding text, using diffusion language models to create text embeddings.
Right. And just as a quick reminder, text embeddings are, well, they're pretty crucial in NLP. They let computers essentially grasp the meaning behind words for tasks like, finding relevant documents or sorting information,
Yeah, traditionally we've seen models like BERT and T5 handle this. They often use something called contrastive learning.
which is sort of like learning by comparison, showing the model what's similar text and what's different. And more recently, of course, large language models, LLMs, have been adapted for embedding tasks too.
But there's a bit of a, let's say, a fundamental challenge with using many standard LLMs for embeddings, isn't there?
There is. It stems from how they're initially trained. They typically predict the next word using what's called unidirectional attention. It's like reading only from left to right, one word at a time.
So it doesn't naturally look at the whole picture, the full context in both directions, which you often need for a good embedding that captures overall meaning.
Precisely. That bidirectional nature, understanding how words relate across the entire text, isn't inherent in that standard pre-training. It struggles sometimes with that global context.
Yeah. And people have tried to work around this, right? Things like echo embeddings or LLM-2-vec.
Yes, there have been attempts, but they often come with trade-offs like making the process slower, the inference overhead, or they haven't scaled up that well to really large models or data sets.
So the question becomes, can we start from a different foundation? A model architecture that is inherently bidirectional.
And that's where diffusion language models come in. They've shown promise in other areas like complex reasoning, partly because they do have this bidirectional architecture built in.
Okay, so our mission for this deep dive is to really unpack how these diffusion models are being used for text embeddings and, what advantages they might actually offer over the current approaches.
Let's start with the basics of diffusion LMs then. How do they actually process text?
Well, the core concept involves taking text and gradually masking out tokens, words, basically. That's the forward part.
Okay, like hiding parts of the sentence.
Right. And then the model learns the reverse, how to accurately fill in those masked out parts, how to reconstruct the original text.
Ah, so it's not predicting the next word like an LLM. It's learning to rebuild the whole thing from a partial view.
Exactly. And the key point, as the paper illustrates conceptually in Figure 1b for a model called DUIM, is that this reconstruction uses bidirectional attention. It learns by looking at context from both sides of a masked word.
Got it. It has to consider everything around the gap to fill it in correctly.
That simultaneous look is crucial. So the paper introduces this new method, Diffembed. It basically takes advantage of this inherent bidirectional understanding from the diffusion LM.
And how does DefEmbed actually create the embedding? It extracts the contextualized representations for each token, the understanding of each word given its surroundings that the diffusion model learns during that reconstruction process. Then it aggregates them, often just using a simple mean pooling, like an average, as shown conceptually in Figure 2, to get one single vector representing the whole text.
So it's a fundamental difference in how the understanding is learned. LLMs use that causal next token prediction focus.
While diffusion LMs use this denoising reconstruction objective, which naturally leads to embeddings that capture meaning bidirectionally.
Okay, that's the theory. How does it stack up in practice? The researchers really put it to the test, didn't they?
They did a really diverse set of tasks. We're talking long document retrieval, tasks needing some serious reasoning, instruction following retrieval, and also the standard text embedding benchmarks.
Let's start with those long documents. That seems like a place where seeing the whole context would really matter.
Absolutely. Traditional models can definitely hit limits with very long inputs. So the researchers trained Diffembed alongside some top LLM-based embedding models on texts up to 4,096 tokens long. They used part of the public E5 dataset for this.
And then tested on the long embed benchmark.
Right. Long embed includes some clever synthetic tests like finding a specific passkey hidden deep in a long document or the class of needle in a haystack, but also real-world tasks like question answering on long text from datasets like NQA or QMSUM.
And the results.
Pretty striking. As shown in Table 2, Diffembed, which was based on the Dream 7b diffusion model, outperformed a strong baseline, Llama 3.8b, on this long embed benchmark by about 20%.
Huh.
That's a significant margin.
Wow, 20%, and particularly on those synthetic tasks.
Especially there. On things like the passkey retrieval, where the key information could be anywhere, Diffembed got near-perfect accuracy. It really suggests that being able to look both ways across the whole document is a major advantage for long context understanding.
That makes a lot of sense. If you can scan back and forth, you're less likely to miss something buried deep inside. Okay, what about tasks needing more complex reasoning, going beyond just keyword matching?
Yeah, this is another interesting area. They use the Bright benchmark for this, which tests if a model can retrieve documents based on, say, logical connections. Think finding the right mathematical theorem to solve a problem, not just finding documents that mention similar terms.
So you need to understand the underlying logic.
Exactly. And they noticed a gap, not much training data specifically designed for this kind of reasoning-based retrieval. So they actually created a new data set called Reasonog.
Oh, interesting. How did they make that?
They used LLMs, specifically GPT-4 Mini in this case, to generate pairs of logically related items, things like a question and the concept needed to answer it, or pairs of related questions across math, physics, and even coding problems. Figure 3 kind of outlines this pipeline.
So building specific training data for reasoning. And how did DiffEmbed do when trained on Reasonog and tested on Bright?
The results, which you can see in Table 3, were again quite positive. Diffembed outperformed Llama 3 8B overall on the relevant Bright subsets by 8%.
Mm.
But the really standout result was on the theorem QA tasks within Bright, a 16.4% improvement.
16% on theorem retrieval. That really points towards the bidirectional context helping with complex logical structures.
It certainly seems that way. Understanding the nuances of theorems and logical steps appears to benefit significantly from looking at the whole context. The improvements on some other parts, like AOPS and leet code, were a bit more mixed, and we can touch on why later.
Okay. Before we get to that, what about instruction following, where the model needs to understand and act on retrieval commands?
Right, this is a growing area. They use the MS Marco dataset that includes instructions for training and then evaluated on the follow-error benchmark.
And the results there.
Here, things were a bit different. Table 4 shows Diffembed performed comparably to Mistral, another capable LLM-based model, no huge leap like in the other tasks.
Any thoughts on why?
The researchers suggest it might be down to the nature of the tasks in follower. The queries and instructions tend to be shorter and perhaps less complex than, say, understanding a long document or a mathematical proof. So the specific advantages of Diffembed's deep bidirectional understanding might not come into play as much.
Okay, so the task complexity matters. And finally, they also looked at the standard, more general embedding tasks.
Yes, they used the Big MT benchmark, which covers about 15 different tasks, classification, clustering, standard retrieval, etc.
And how did DiffEmbed fare there?
As Table 6 shows, it performed pretty much on par with the established LLM embedding models. Again, this seems to suggest that its real edge comes out when tasks demand deeper understanding of long-range dependencies or complex reasoning, more so than on some of the shorter text, less reasoning-intensive standard benchmarks.
That paints a pretty clear picture. The benefits seem quite context-dependent. The paper also dug into why these results occurred, right? Like why general models sometimes struggle with reasoning.
It did. That was Q1 in their analysis. They found that models like E5 Mistral, if not specifically trained for reasoning tasks, like with Reasonog, tend to fall back on more superficial cues. They match semantic similarity rather than grasping the underlying theorem or logical structure needed.
Yeah.
Figure 5 has some visualizations, and Table 10 gives qualitative examples of this.
So they match words, but not necessarily the core logic.
Pretty much. And Q2 directly tested the importance of that bidirectional attention.
How do they do that?
Through an ablation study. They essentially switched off the reverse attention mechanism in both Mistral and Diffembed and reran the tests.
And
The results in Table 5 are quite telling. While Mistral's performance dipped slightly, Diffembed's performance on the Bright reasoning benchmark dropped substantially, especially on theorem QA. It really underscores how much Diffembed relies on that bidirectional processing for these logical reasoning tasks.
makes sense. It's core to its architecture. Now, what about Q3, the less dramatic improvements on those leet code and AOPS reasoning subsets?
Yes. The analysis there, detailed in Tables 8 and 9, suggests issues within the datasets themselves. They found potential noise and inconsistencies in the gold standard annotations and the documents.
It's like the definition of what's relevant wasn't always clear.
Exactly. For instance, in leet code, sometimes relevance seemed based on contextual similarity, other times on algorithmic similarity between problems, like trapping rainwater 1 and 2 being linked despite different contexts. Table 12 even shows an example of a document label relevant that seemed pretty noisy or off-topic. So dataset quality might be blurring the picture a bit there.
Right, noisy evaluation makes it hard to see true performance. And the last point, Q4, was about training data size.
Yeah, they looked at how performance on Theorem QA changed as they varied the amount of training data, shown in Figure 4. The results suggest that LLM-based models might need significantly more reasoning-specific data, like ReasonOg, to learn effective bidirectional patterns compared to DiffEmbed, where bidirectionality is sort of baked in from the start via the diffusion objective.
Interesting. So diffusion models might be more data efficient for learning these kinds of complex relationships.
That seems to be the implication from this particular study.
Okay, so wrapping up this deep dive, the key takeaway seems to be that these diffusion language models, like the one used in DiffEmbed, show real promise for text embeddings, especially for tasks that involve understanding long, complex texts or require significant logical reasoning.
Absolutely. That inherent bidirectional architecture appears to give them a distinct advantage in those scenarios. And the creation of the ReasonOg dataset is also a valuable contribution itself, potentially helping future research in reasoning-based retrieval.
Of course, the researchers acknowledged limitations. They primarily looked at one diffusion LM architecture, Dream, and there are always questions about training scale.
True, it's early days for this specific application, but it definitely opens up some thought-provoking directions.
Which leads us to our final thought for you, the listener. Given how effective this bidirectional approach seems to be for embeddings in complex tasks, what other areas of NLP currently dominated by autoregressive next word prediction models might see significant gains if we started applying similar diffusion-based bidirectional techniques? Where else could this reconstruction approach unlock new capabilities?